Okay, good evening, everybody. And welcome to the first online review session for the spring 2014 semester. In today's session, we are going to review for the first exam, which is scheduled for Thursday, February 6th. And for this session, we are going to use the EXAM1 question that was used in the spring of 2013. Notice that a lot of you have joined us already. I will be acknowledging all of you during the course of this session. But before we start the session, let me point out a few of the functionalities on this virtual classroom. Now, if you want to pick up the mic and ask me a question through the your mic, you click on this icon here. Can you guys see this icon? If you can see this icon, give me what I call a happy face. Go to here and click on this here to give me a happy face. If you can see my cursor right here. Okay, very good. Okay, now, if on the other hand, you want to share your video with the rest of the class, you could click on this here, this icon here that says video, and then we will be able to see your video. Okay, on the talk icon right here, whenever you finish talking, make sure you click on it again in order to disable your mic. That will allow other students to join the session by also wanting to ask questions. Now, in case you want to simply send me questions through the chat window or to interact with the rest of the class, you could right here send me a chat or a question through here. For example, I could simply say good evening here. And then you enter, just click on the enter, and then everybody will see your comment. Okay. In addition to the icon here, if you want to ask me a question or you want to raise your hand electronically, just click on this electronic hand right here. Okay. And then, if you want to leave the session for a few minutes, you want to let me know that you will be gone for a few minutes, just click on this icon right here. Okay, so now at this point, let us start the session. So what I want to do now, I will go to the first question. Okay, to read the first question for us, let me call on Masha K. Can you read this question for us?
Provide the missing reagents in the following synthetic scheme.
Okay, very good. But before you leave before you turn off your mic, let me also ask you to assist me in solving the first part of this question, which is this one here. Okay, it says provide the missing reagent. Okay, so let us solve this together. You and I solve this together. So what is going on here? What do we need to do here?
Friedel-Crafts alkylation.
Okay, you say that is Friedel-Crafts alkylation. Very good. Okay, and for Friedel-Crafts alkylation, in this particular instance, what exactly are we doing?
Adding CH3Cl in the presence of aluminum chloride, AlCl3.
Okay. Okay, very good. So in other words, you are going to use this reagent here, okay, methyl chloride in the presence of aluminum chloride as a catalyst. And when you do that, this methyl here will replace the one of the hydrogen on the benzene ring, and now you form your toluene. This molecule is called toluene. Okay, and this reaction here, this is called a Friedel-Crafts alkylation. Okay, you can see here, essentially what you need to do here, you need to know your reagent. Okay, so you need to know all of the reagents that you need for most of these reactions in organic chemistry. Okay, thank you, Marcia. So let me now call on the rest of the class to assist us in solving the rest of the questions. By the way, if you all understand what Marcia K just told us, can you give me a happy face? Okay, in other words, this is a Friedel-Crafts alkylation. Very good. Okay, now let us do the next one. B. What reagent do we need for B? You notice here, take this out of here. Okay, so you notice here, we are going to replace this hydrogen here with the sulfonic acid group. So what reagent do we need? Can you all send this to me to the chat window? Or okay, excellent, excellent. Okay, okay, very good, very good. Let's see here. Say sulfur trioxide and sulfuric acid. Excellent, very good, very good. Okay, so this is sulfur trioxide in the presence of sulfuric acid. By the way, if you feel like, you could pick up the mic if you want to answer the question also. Okay, so that is correct. Okay, how about C? How about C? What reagent do we need to go from here? In this case, what are we doing here? We are going to transform this methyl group to the carboxyl group. Somebody has a question for me. Okay, Jamal, can you go ahead and ask your question? You could type the question or you pick up the mic. Oh, okay, I got you. Okay, you want to answer the question. I see your answer. Very good. Excellent. Okay, so Jamal has given us the answer here. Say we need to use potassium permanganate. Very good. Okay, thank you. Okay, and generally you use potassium permanganate in the presence of acid, dilute acid. Okay. Oh, I'm sorry. Right here. Take that out. Right here. The presence of dilute acid. Okay. Okay, now let us do D. What reagent do we need for D? Any volunteer for this? Oh, by the way, all of you could simply send me your text message to answer this question, any given question. Okay, nitric acid. Okay, very good. And what? Yes, sulfuric acid. Very excellent, excellent, excellent. Very good. Okay, I see here. I see Shante Smith. I see Kiara Wallace. I see Victoria Lassing. Okay, you are all welcome. Okay. So what do we need here? We need for here, since we are going to do nitration, so the reagent you need for nitration is nitric acid in the presence of sulfuric acid. Excellent. Okay. So I think you guys have mastered most of these reagents. That is essentially what you need to do. You need to know what these reagents do. You need to know what reagents to use for a particular transformation. So excellent. Now let us go to the next one. Okay, now, right now, I do not know how many of you have a working mic, but if you have a working mic and I do not call on you, you could pick up the mic and ask a particular question. That way I get to know whether your mic is working. Okay, Kiara Wallace, can you go ahead and read this question for us?
Provide the missing reagents in the following reaction sequence.
Okay, thank you. It said provide the missing reagents in the following reaction sequence. Okay, turn off your mic. Turn off your mic. Okay, so provide the missing reagents in the following reaction sequence. Okay, let us do the first one. What are we doing here? What type of reaction is this? From benzene to this molecule here. What type of reaction is this? Anybody know? What are we doing here? We are replacing this hydrogen here with this AC group. Okay, acylation. Excellent, excellent. So this is called Friedel-Crafts acylation. Friedel-Crafts acylation. Okay, so that is good. Friedel-Crafts acylation. Okay, so therefore, what reagent do you need for this particular Friedel-Crafts acylation? How many carbon atoms in that reagent? How many carbon atoms? 3. Okay. Okay, do you need a carbonyl group in there? Yes or no? Yes. Excellent. Excellent. Very good. Very good. Okay, let us now do this. Okay, so we need this here. So we use this here. We use what we call an acid chloride in the presence of aluminum chloride as a catalyst. And what this will do is to substitute, replace this hydrogen here with this AC group, and that is what you have here. Very good. How about B? What do we need to do here? What are we doing in B? What are we doing in B? Look very carefully here, from the starting material to the hydrogenation. Excellent. Okay, now, what does the hydrogenation do? That is correct. What does the hydrogenation do? I see Alexis, I see Shante, I see Masha K. Very good. What does the hydrogenation do? Be very specific now. What does it do? You have a carbonyl that is attached to benzene, will be transformed to a CH2. So we call this a methylene group. So anytime you have a carbonyl of a ketone or a carbonyl of an aldehyde that is attached to benzene, if you perform hydrogenation, in which case you use this reagent here, hydrogen in the presence of a catalyst, let us use palladium. Okay, what you do is to transform or to reduce the carbonyl to a CH2 or to a methylene group. Very good. How about C? What are we doing in C? What are we doing? Okay, very good. Okay, I see Jamal, thank you. What are we doing in C? Okay, okay, bromination, excellent. Okay, Jillian, you are welcome. Okay, Mashake, bromination, Alexis, very good, excellent, excellent. So therefore, you say we are doing bromination. Okay, so let us take this out of here. And to do bromination, what reagent do you need for bromination? Okay, you already given it to us. You say bromine in the presence of iron 3 bromide. Okay? And this is the reagent you need for bromination, okay? Okay, so therefore, and this group here, this alkyl group, this is an auto para director, okay? In other words, it will direct an incoming group to either the para position or the auto position, okay? In this case, they are asking for the para product. Very good. Okay, about D. What are we doing in D? What are we doing in D? And what reagent do we need? What, okay, if you notice here for D, what are we doing? Okay, what is happening here? We are replacing this one of these hydrogen here, one of the benzylic hydrogen attached to the benzylic carbon with a bromine atom. Okay? So this is a form of bromination also. So therefore, what reagent do we need to do that? To replace, okay, excellent. Okay, excellent. Victoria, thank you. Okay, so you use MBS. MBS in the presence of a peroxide. You could use any peroxide, by the way. Okay, MBS in the presence of peroxide and light. Okay, and that will replace the benzylic hydrogen. That is the hydrogen attached to the benzylic carbon. It will replace that with bromine atom. Okay, and that is what we have here. Okay, very good. So far, so good. How about E? How about E? What are we doing here? Okay, elimination. Okay, Olulade, you are welcome. Okay, okay, yes, Kiara Wallace, you are also very good. Very good. You say bromine. Okay, elimination. So we are going to use potassium hydroxide. Let me put that here. Very good. I think you guys are getting ready for this exam. Use potassium hydroxide. Okay. Okay. Is there any question on this before we move? Go to the next one. No question. Okay. Let us go to. Okay. Cynthia Jaffo, can you read this question for us?
Starting with benzene, draw the synthetic scheme for the following compounds.
Okay, thank you. Okay, so in this question here, they want you to start with benzene. This is a syntactic problem, unlike the other problem that we gave you, in which you simply need to know your reagents. Okay, so starting from benzene, they want you to go from benzene and then make this compound here. So in this type of question, you need to know your reagents, and then you need to be able to put together a series or sequence of reactions that will ultimately give you this product starting from here. That means you need to use some, what I always refer to as critical thinking skills at this point, okay? Okay, so let us start. I need your help now. Okay, let us start. We'll start with benzene. But before we do that, let us do a little bit of analysis. Okay, what do we have here? We have a methyl group on this molecule here. So therefore, we need to replace an hydrogen on benzene with a methyl. So you guys know what we need to do for that. Then we need to introduce a nitro group to the para position. We know that this group, methyl, is an auto para director. And then also we need to introduce a bromine. Okay, so let us put this together. Can you tell me what is the first thing we need to do? What is the first thing we need to do? Okay, I need your help now. What is it? We've done some of this already in the previous question. Okay, alkylation. Okay, very good. Friedel-Crafts alkylation. Excellent. Okay, Victoria, Mashake. Okay, both of you are correct. Very good. So you want us to do, okay, Gillian. Okay, very good. Excellent, excellent. So you want us to do Friedel-Crafts alkylation. Okay, so that would be this. So in this case, you just simply need to know those reagents, but once you know them, you need to be able to put all of this together in a synthetic scheme. Okay, now we have the toluene. We have replaced the hydrogen here with methyl. Now, what is the next step? What is the next step? Okay, bromination. You want to do bromination? Or nitration? Okay. Okay, let us do nitration. Very good. Nitration. Okay. And that is nitric acid in the presence of sulfuric acid. And so we know that the methyl is a auto-para director. We want the para product, so we are going to place the nitro group in the para position. Oh, by the way, during the course of this session, if I lose my internet connection, you guys should just stay where you are. I will join you very shortly, okay? Okay, so now we have the nitro group right here. Okay, so now what is the next thing we need to do? Come to here. Bromination. What reagent do we need for bromination? What reagent do we need for bromination? Bromine in the presence of, very good. Keep in mind, it is bromine in the presence of the iron 3 bromide, not bromine by itself. Keep that in mind. Okay, so we have solved that problem. That problem is solved. Okay, so let us go to the next one. I think we are moving right along. Hopefully, we will be out of here in about 1 hour. Okay, now we have a mechanistic problem. Okay, now, if your mic is working and I've not called on you, can you read this question for us?
Provide
Just pick up the mic.
Provide
Yes,
a mechanism for the following transformation.
Okay, thank you. That's Dideolu. Very good. That will do. Okay, very good. So now you say provide a mechanism for the following transformation. Okay. Now let us take a look at this. We need to do some analysis here. To help you out, I am going to number this carbon here. Let us say this is carbon 1, carbon 2, carbon 3, carbon 4, and I am going to call this carbon 5, carbon 6, carbon 7, and carbon 8. Now, when you come to this product here, let us go ahead and number those carbons. This is carbon 1, carbon 2, 3, this is 4, this will be 5, this will be 6, this is 7, and this is 8. Now, if you look at this here, what does this tell you? Keep in mind, I will give you a clue. This is a modification of the Friedel-Crafts alkylation. So, I will say a modification of Friedel-Crafts alkylation. Now, let me ask you this. Since I've told you this is a modification of fiddle-crab alkylation, what kind of nucleophile do you have in fiddle-crab alkylation? What kind of nucleophile? Can anybody tell me just what kind of nucleophile do we have in fiddle-crab alkylation? What kind of nucleophile do we have in fiddle-crab alkylation? Anybody has an idea? Okay. Any? No. Okay. Nucleophile in fiddle-crab alkylation. Okay. Say you have this. Maybe I will help you out here. No. Keep trying. Keep trying. Okay, if you have fiddle-crab alkylation, okay, you start with an alkyl chloride, right? And then you start with aluminum chloride. And we told you in fiddle-crab alkylation, the aluminum chloride is acting as a catalyst and also is a Lewis acid. So this comes here. The chlorine attacks the aluminum, and what do you get? You get this complex here. Okay, very good. A carbocation. Okay, Olulale said a carbocation. Excellent. That is exactly what you get. You need to know that. Okay, but since you've already told us that we are going to get a carbocation as the electrophile. I'm sorry. Did I say nucleophile? I think maybe I misled you here. I meant to say electrophile here. Maybe that was my... Okay, maybe that was why you could not get it. Okay, I meant to ask you, what is the electrophile that you need for in the fiddle-crab alkylation? Okay, so now, so you have this, and then what we have this here. Okay, and now as a result of the fact that we have now donated the electron to this aluminum, that will weaken this carbon-chlorine bond so that you are now going to have this. This bond will break, and then you get the carbocation. And now you get your carbocation, okay? Okay, so therefore, in all of the fiddle-crab alkylation, you do, your electrophile is a carbocation. So if I told you that this is a modification of the fiddle-crab alkylation, the difference here, we are not using an alkyl chloride, we are using an ether. Okay, that is the difference. But the point is that we are going to go through the formation of a carbocation. Okay? So I haven't given you that information. What will be the mechanism of this reaction? What will be the mechanism of this reaction? Let me ask you, maybe I should ask you a simple question. Okay, do you expect this here, since we are going to join this carbon here to this here, do you expect us to form a carbocation on carbon number 1? Yes or no? Just give me yes or no. Do you expect a carbocation here? Yes, very good, excellent, yes. Do you also, since we are also going to join this carbon number 4 to this carbon here of the benzene, do you expect us to form a carbocation on carbon number 4? Yes or no? Okay, yes, okay. Now, if that is the case, Now, let's see now. Let us now do this. If that is the case, then we say the first thing that is going to do, whatever we need to do, we need to find a way to form the carbocation. So you see here, sulfuric acid is here. Sulfuric acid will be donating a proton, it's an acid. So we have this acid here. And we also know that this oxygen has non-bonding pair of electrons, okay? So what do you think is going to happen now? Can anybody tell me what will happen? This will be acting as an acid. What will happen? And oxygen here will be acting as a base. So what is going to happen? Anybody tell me? Where should my arrow go? From where is my arrow going to the proton here? Okay, I want to draw an arrow because when you are asked to give the reaction mechanism, you need to show the arrow showing the movement of electron. So you have this electron here attacking the proton, right? So therefore, we are going to form this. So the first thing that we need to do here is to show how we form the electrophile. So now this oxygen is now positively charged. Now, once that oxygen is positively charged, now we could now have, we are going to now break this bond because that will weaken the carbon-oxygen bond or this carbon-oxygen bond. So we could break any one of them. Okay, so now, say, okay, we do that, and therefore we have this. Now the carbocation is on carbon number 1 at this point, right? Okay, so let us number our carbon here. These are carbon 1, 2, 3, and 4. This is 5. This is 6. This is 7, and this is 8. Now, what do you think is going to happen now? Does anybody now know what is going to happen now? We have formed our electrophile. What will happen now? Now, what do you expect to happen? Okay, very good. No, not hydroxide. Double bond of the benzene will attack the electrophile. Excellent, excellent. That is what is going to happen now. Now, the pi electron in benzene now come, because now this is now going to act as an electrophile. Okay? Does that. Keep in mind that we have hydrogen here to start with. Okay? So now what we have this. Okay. Okay, so now we have that. We have, this is going to still be here. This is still here. The positive charge will be here. And this hydrogen is here. And then we have this here. This here. This here, this here. This is here, this is here. And then we actually have this here. Okay. Let us go ahead and number our carbons. This is carbon 1, 2, 3, and 4. This is 5. This is 6. This is 7. This is 8. Okay, and now at this point we form this intermediate carbocation here. So now we are going to have, keep in mind that when we form this, when the proton donated the sulfuric acid donated the proton, we also form this here. That will be acting as a base. So that comes in now. Comes in to grab this proton here. Now let me change the pen color. Grab this proton here. Oh, I'm sorry. Yes, grab that proton, and let me write that proton close to the benzene. Doesn't look like it's so far away from it. This relay here. Okay. And now we regenerate the double bond right here. Okay. So we form this. Okay. Okay. Now, what do you think is going to happen now? What is going to happen next in order to complete this process? Does anybody know what is going to happen now? Any idea? Okay. Okay. But before it loses water, yes, you're on the right track. You're on the right track. Before it loses water, you cannot just lose water. This is OH right here. Protonation, okay? Protonation, not hydrogenation. To be protonation. Now you are going to get another proton from sulfuric acid. Keep in mind that the sulfuric acid here, we are forming sulfuric acid here. That is why we call this a catalyst. Okay. So now we get a protonation from sulfuric acid again to protonate this here. Sorry. This electron goes. Notice our arrow, you draw arrow from electron to the electrophile. Okay, and once you do that, you now form this product. Yes. Okay, Jamal, go ahead and ask your question.
At this step of the equation, wouldn't the hydrogen or the sulfur group be H2 or H3SO4 if it's donating a hydrogen?
Yeah, but the sulfuric acid, we start with H2SO4, right? When it donates the hydrogen, it becomes HSO4 minus. Okay? And that HSO4 minus comes here to grab this proton again. Now it goes back to H2SO4 again. Now again, it will now also donate another proton to this here. Okay, so now we have donate a proton to this oxygen again. Now that becomes positively charged. And then this is still here, right? At this point now we lose water. Okay, this is the point at which we lose water. Take this out of here. Okay, you notice here, whenever you are doing a reaction mechanism, that takes understanding of the process, okay? Okay, now we lose water. This is when we lose water. Now we lose this as water. In other words, we are going to break this oxygen-carbon bond, okay? And that gives us this here. So now this now becomes a carbocation. Keep in mind, once we lose this water here, now we are going to form a tertiary carbocation right here. Okay, of course, this is water here. Okay. Now, what is going to happen now? What is going to happen now? We will now form another electrophile. What is going to happen now? Okay, I need your assistance here. What happens at this point? Okay, double bond attack, exactly. The pi electron in benzene attacks this carbocation. Excellent, excellent. Okay, excellent, okay. Okay, okay, so the double bond will attack. Let us see here. So we now have this attack. This carbocation is attacked. And then we have this. Keep in mind that, let me also show that we have right here, we have an hydrogen here, okay? So, what do we have? We now have this. Oh, sorry. This is not here yet. Okay. Once this pi electron attacks this, now you are going to form a positive charge on this carbon here. And of course, you have hydrogen here. So now, at this point, another base from sulfuric acid, this here, will now come in and grab the proton. Come here to grab this proton here. And that will therefore release the pair of electrons to form a pi bond. So now we are going to regenerate the benzene ring. Okay? Okay, so let us number our carbon here. This is our carbon 1, 2, 3, 4. This is 5. This is 6. This is 7. And this is 8. Now, if you follow the mechanism that we have just given you, give me a happy face. If you follow that mechanism, give me a happy face. Keep in mind, whenever you are doing reaction mechanism, you need to just take your time, draw an arrow from where you have electron to where you have a positive center, okay? In other words, you got to show how the reaction takes place step by step, okay? Okay, anyway, so this is the reaction mechanism for this product here. Okay, somebody asked a question. Okay, is that Jamal again? Yeah, go ahead and ask your question.
Okay, it looks like the mechanism always goes from the nucleophile to the catalyst back to the nucleophile. Is that what you want us to do when we do it on the test?
Well, I don't want to make a general statement like that, but yeah, but you are on the right track. Whenever you draw in reaction mechanism, the arrow generally goes from your nucleophile to the electrophile. Keep in mind the nucleophile contains electrons. The electrophile is positively charged, or a center that could develop a positive center charge. So that is the general thrust of reaction mechanism. You need to draw those arrows, but the arrow must flow from where you have the electrons to where you do not have electrons. That is the basic, the underlying concept of reaction mechanism. Okay, so in this particular instance here, what we've given you here is the mechanism from how we go from here reacting with this in the presence of folic acid to obtain this here. You notice that in that reaction mechanism, we are using every one of these reactant, reagent, and catalyst in order to get to the final product. Okay? And that is what we've done here. From here to here, all the way to here, and finally to here. Okay? Okay, so let us go to the next one. Okay, okay, Jamal, can you go ahead and read this question for us?
On mononitration, which compound would yield the highest para to ortho ratio?
Okay, thank you. Very good. Okay, so this question is asking us on mononitration. In other words, we want to do a nitration here. In other words, replacing an hydrogen with the nitronium ion. Which compound will yield the highest para to ortho ratio? Another way we could ask this question here, which of these starting material here will give you more of the para product? That is another way of asking you that question. Which one of these here will give you more of the para product? Okay, so this question is assuming that you know the structure for all of these compounds. Okay, the structure for this is toluene. So you need to know the structure for this in order to answer this question. Okay, and this is Ethylbenzene. And this here is Isopropylbenzene. And this here is tert-Butylbenzene. Okay, so what is the correct answer here? In other words, it is asking you which one of these compounds here will give you the highest para to ortho ratio. Another way to ask you that question is, which one of these will give you, which one will give the most amount of para product? Upon nitration. Keep in mind all of these here we are reacting with nitric acid, okay? In the presence of sulfuric acid, we are doing sulfonation. We are doing nitration. Okay, so the product that we expect to get if we use this, for example, because each one of these here, each one of these substituent is an auto-para director. Okay, so what will be the correct answer? Which one will give you most para product? 4, excellent. That is correct. Why? That is correct. 4 is correct. Why? That is correct. This will give you the most para product. Why? Steric hindrance. Okay. Okay, very good. Okay, very good. Okay, that is correct. You are correct. It's because of steric hindrance. Because of steric. Hindrance, or sometimes we call steric as strain. Okay, if you look at this, look at all of these here. Of all you have of all the substituents, you have the methyl, ethyl, isopropyl, and then the tertiary butyl. You notice here, the tertiary butyl is the biggest of all the substituents, is the bulkiest. Okay, and as such, it will prevent any incoming group coming to the auto position, because there will be interaction between this group here and the incoming groups. Therefore, most of the product will be directed to the para position, and that is because of steric hindrance. Okay, so I think all of you got that right. Very good. Go to the next one. Okay, I think we did this in class, so we don't need to do this right here. Anybody who has any problem with this, you come and see me in the office. Okay, but let's do a little bit of nomenclature. A little bit of nomenclature, okay? If your mic is working and I have not called you or you have not talked to me tonight, can you pick up the mic and read this question for us? Okay, no volunteer. Okay, let me just call on Masha K. Can you go ahead and read this for us?
Draw structures corresponding to the following names.
Go ahead. Continue.
A, 3-chlorobutyl aniline. B, 3-bromo-2-methylbenzoic acid. C, 4-isopropyl, 3-nitrobenzaldehyde. D, 4-chloro, 2-propylbenzene sulfonic acid.
Okay, very good, and thank you. Okay, so what do we need to do here? You can see here, let us start with this. The base name for this molecule is aniline. Okay, aniline is this structure here. So, okay, we need to know the base name first. That is aniline. Okay, this molecule is called aniline. Now, it says P3-chlorobutyl. So that tells us that this group here is in the para position. So we have to do this. There is a group in para position. It is a complex group. You notice they put this in parentheses, right? Okay, 3-chlorobutyl. So that means you have a butyl group, CH2, CH2, CH2. Butyl means 4, right? Butyl means 4. Okay? So it says 3-chlorobutyl. Now, whenever you have a side chain that is attached to the main structure or the base name, if that side chain is also attached to a substituent, what you do, you number that side chain from the position where it is attached to the base name. So we are going to call this carbon 1, carbon 2, carbon 3, and carbon 4. Now, they also tell us 3-chlorobutyl. That means that the chlorine is on the 3 carbon of this butyl. So what do? We remove this hydrogen here, and we replace with chlorine. Okay? So therefore, this is the structure of P3-chlorobutyl. Because they put this in parentheses, that tells you this is a complex substituent. Okay, and the way you deal with that is to number the substituent, give the substituent, the carbon of the substituent numbers, such that the carbon that is attached to the base name will be carbon number 1. Okay? Okay, if you follow that, give me a happy face. That is this here. Okay, very good. Okay, now let us do this. 3-bromobenzoic acid. Does anybody, okay, the base name for this is benzoic acid. Does anybody know what the structure of benzoic acid is? Any idea? What is benzoic acid? That is the base name. Benzoic acid. Okay, very good. Okay, benzene with carboxy. Excellent, excellent, excellent. Okay? Okay, so you guys say this is this here, benzene with carboxy group. That is benzoic acid. Now they say 3-bromo. That means the bromine is in the 3 position of benzoic acid. And then the 2-methyl. Okay? Okay, so that becomes, keep in mind, whenever you have this carbon here that is attached to the carboxy group of benzoic acid becomes carbon number 1. Okay? And therefore, this is 3-bromo, 2-methyl benzoic acid. Very good. Now let us do this. Okay. This is 4-isopropyl 3-nitrobenzaldehyde. Again, you identify the base name. So the base name is this here, benzaldehyde. So that means we have this. That is your benzaldehyde. And now we have in the 4 position isopropyl, we have this here. This is your isopropyl group. And then in the 3 position, you have your nitro. Okay, so this is position 1, 2, 3, and then 4. Okay? And finally, let us do this. 4-chloro, 2-propyl benzene sulfonic acid. Again, to do this, you identify the base name, and this is your base name right here. That is benzene sulfonic acid. So you need to know the structure of benzene sulfonic acid, which is this here. Okay. Now you say 4-chloro, 2-propyl. Okay, propyl is in the 2 position. And then 4-chloro. Okay, so nomenclature, all of you guys should not have have problem with nomenclature. I think that is probably one of the simplest part of organic chemistry. Okay, so let us go to the next one if you do not have any question on this. Okay. By the way, what time do we have? Okay, 9:01. Okay, let us spend about 10 more minutes and then we call it a day. And then tomorrow, we will finish up the rest of this tomorrow. Okay? That is in class after the quiz. Okay. Another nomenclature problem. Okay, Kiara, can you go ahead and read this for us if your mic is still working? Kiara Wallace.
Give IPEC names for the following structures.
Okay, thank you. Now, so what is the base name for this? What do you want to use for the base name for this? Let us do this one first. This one. What do you want to use? Okay, let us say we use aniline. I want to use this part of the molecule for the base name. That is aniline. Okay? So that becomes 3. Oh, okay, thank you. Okay, you guys already giving it to me. Okay, do you want to give me the name also? Go ahead. 3-ethyl aniline. Okay, very simple. Okay, let us do this one here. Okay, for this, I want to use for the base name. I want to use benzoic acid. I want to use this for the base name, benzoic acid. Okay? Okay, so what will be the name for this? You have to give the number so that you assign the lowest possible number to the substituent. So that becomes, I will say this is carbon 1, 2, 3, 4, 5, and 6. So that becomes, okay, 1, okay, you say 1, okay, 2, 5, very good, 2, 5, that is 2, 5, dinitro benzoic acid. Excellent. Okay, very good. Excellent. Okay. Keep in mind, you give the lowest possible number to the substituent. Okay, so let us do this one here. For this one here, I will advise that you just use benzene as the base name. Use benzene for the base name. So if you are going to use benzene for the base name, which is going to be carbon 1, where are you going to start carbon 1 from? From bromine or from, okay, good. Bromine becomes carbon 1 because you have to use the alphabetical order. So this becomes 1, therefore this becomes 2, 3, 4, 5, and 6. So this becomes 1 bromo, 3, 5 dichloro benzene, because we are using benzene as our base name. Okay? Now let us do this. So this one is this one here. Let us do this. Okay. In this case, if you take a look at this, anytime you have the benzene ring attached to a chain, and if that chain has 6 or more carbon atoms, okay, what you want to do therefore is to make the benzene ring a substituent. In that case, the benzene ring will be called a phenyl. Become phenyl group. Okay, just as you have methyl or ethyl. So this becomes phenyl. Okay, so therefore, let us go ahead and, okay, let me ask you this. What would be the base name for this molecule? What would be the base name for this molecule? Hexane. Excellent, excellent, very good. Hexane. Okay, so let us number it. Carbon 1, carbon 2, 3, 4, 5, and 6. Okay, so therefore that means you have substituent in position 2, which is your phenyl, and another substituent in position 5, which is methyl. Okay, let me see here. We need to, there's something I'm missing here. Let me look at my alphabet. LMNOP. Oh, okay. In that case, we have to start numbering from here because the M comes before P. Okay. Keep in mind, if you number from here, anytime you are going to assign numbers, and you could assign the same number coming from the opposite direction, in that case, you got to assign numbers based on the alphabetical order of the substituent. So, in that case, what we need to do, so this would therefore become, this will now become carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. So therefore, we are going to call this 2-methyl. Keep in mind, M comes before P. 5 phenyl hexane. Okay, somebody asked a question for me. Did he go ahead and ask your question? You could type it in the chat window. Yeah, go ahead.
You said it has to be how many carbons for it to be phenyl?
Yeah, if you have, anytime you have 6 or more carbon attached to benzene, then you could use benzene as a substituent, okay, in that case. Sometimes you may even, when you have 5 carbon attached to benzene, sometimes you also use benzene as a substituent. In that case, you call it a phenyl. So in this case, we are using benzene as a substituent, okay? So in this particular instance, therefore, the name is this 2-methyl 5-phenyl hexane. Okay. Okay, let us do one more question and then we call it a day. I think that is question number 8. Yes. Okay, Jamal, go ahead and ask your question. You may want to type it if your mic is not working. Okay, could you also say M? Oh, no, you cannot do that because you keep in mind that we are, in other words, you want to use the meta nomenclature. No, you cannot do that because do not forget here, benzene is, we are using benzene as a substituent. Okay? Okay. Okay, so let us do one more question. Okay, let us do this and then we call it a day and then we finish the rest of them, these questions in class tomorrow. Okay, I think after this I got one more question I want you to do. Okay, let us see here. Cynthia Jaffo, can you read this question for us?
Propose the structure for a compound with formula C9H12 that only gives 2 monochloro compounds when it undergoes electrophilic aromatic substitution reaction. Write structure for the product C9H11Cl and write the reagents needed for the reaction.
Okay, very good and thank you. Okay, so now this is one of those roadmap questions. Okay? So what we have here, we start with a molecule C9H12. Does anybody know the index of halogen deficiency for this molecule here? 4. Okay, very good. 4. Okay. Plus, they've already told us this reaction will be going through the monochlorination. Okay, when it undergoes electrophilic aromatic substitution. So they've already told us this is an aromatic molecule. Chances are this is benzene. And what did they say? They say compound A only gives two products. Okay, let us call that B and C, monochloro product, and the formula is C9H11 and chlorine. The same thing here, C9H11 and chlorine, and of course we start with C9H12. Okay. So we know we are dealing with benzene. Okay, so therefore, what kind of combination of structures can we give here? Let me help you out here. I would say the molecule has got to be this. Okay, you know that it is benzene. Okay, benzene, we have 6 carbons here. We only have 3 more carbons to go, right? Okay, so it could be a methyl here. It could be an ethyl here, right? Okay, if you react this with chlorination, you say chlorination. This will only give you 2 products. You will get either here, this here, because of the nature of the starting material that I've just given you. It's a monochloro product, either this or this. So this is a case of actually using some critical thinking skills. Okay, oh, I'm sorry, this is all this. Okay, do you see any other possibility here? Does anybody see any other possibility? I mean, this is what I say. Okay, the formula is of this here, C9H12. The formula for this is C9H11 and chlorine. The same thing here. This one here, C9H11 and chlorine. That is the only possibility that I see here, right? Anybody see any other possibility? Could you have benzene ring with 3 methyl? Okay, okay, that is a good one. That's a good one. Okay. Excellent. Okay. Excellent. That's a good one. I was hoping somebody would make a contribution. Very good. Very good. Can we have this? Somebody, okay, that's Victoria, says, can we have this? Is this a possibility? Let us see, is that a possibility? Okay, if you have, it depends on how we arrange this now. Supposing we have, okay, well, if you are, well, okay, supposing we do this, that could work. Supposing we do this, okay, in that case, we could get this. We could get this. Okay, chlorine here, right? And since this carbon and this carbon and this carbon are This is symmetrical molecule are equivalent, so we could also have this. We could also have this. Okay? This is also a possibility. Okay? On the other hand, if you have this here, that's very good suggestion. If you have this, or this, or this will not work, but this will work. Okay? Very good. So this will work, and this will work. Now, if you follow that, give me a happy face. Okay, 1, 2, 3. Yes, very good. If you follow that, give me a happy face. Very, very good. Okay. Okay, let me see. There was one more question I want us to do before we leave. Let me see if I can find it. Not that one, really. Not that one. We did that in class. Not that one. Not that one. We will do that tomorrow. We did that already. We did that. No, not that one. Okay, let us do this. Let us do this one here, and then we call it a day. Okay, Didel Luke, are you still there? If your mic is still working, can you read this for us?
Okay, starting from benzene, provide a synthetic scheme for 2-bromo-4-ethylbenzene sulfonic acid.
Very good. Oh, very, very good. Okay, so now what do we need to do here? This is a synthetic problem. So starting from benzene, you do this and then we call it a day. Okay, say do this here. Okay, benzene sulfur ethyl. Okay, ethyl, okay. Oh, can you turn your mic off? Turn your mic off. And 2-bromo. Okay. Okay. Want us to go from benzene to this here. Let us take a look at this very carefully. Look at what we need to make here. An ethyl group, which is an auto-para director. A bromine, which is an auto-para director. So this is going to be very difficult having to make this here in which, okay, you have auto-para director, auto-para director. So we need to do something here. And then, of course, we have the sulfonic acid group. Okay, so how do you want to approach this? Keeping in mind that you need to have a meta relationship between the bromine and this ethyl group, both of which are auto-para directors. Okay, so how do we start? Okay, give me some help here. Alkylation. Okay, you say alkylation. Okay, do you really think that? Okay, acylation. Yes, exactly. Okay, that's what okay, acylation. You need to do acylation. Okay, you take benzene, you do Friedel-Crafts acylation. Friedel-Crafts acylation, which is use this acid chloride here, called acid chloride. In the presence of aluminum chloride, so you get this. Notice here, when you are asked to give the synthetic scheme, you don't need to give the mechanism, okay? Okay, so we now have this AC group attached to benzene. So now what do we want to do now? Now, what do you want to do once you do that? This is good. Bromination, excellent. Okay, now you want to do bromination. Because at this point, you know that this group is a metal director. So the choice of sequence is most important in this particular problem. So now you do your bromination. Knowing that this is a metal director, so therefore, okay, so the bromine goes here. Now what do we do now? Now what do we do now? Oh, no, you don't want to do sulfonation because you want the sulfonic acid group to come here. Okay, this is a metal director. Reduction, excellent. Hydrogenation, very good, very good. Okay, that's Jamal said reduction, very good, excellent. Hydrogenation, okay, Machake, Narika, say, okay, very good. Okay, so we do hydrogenation. Using a catalyst, in this case, you could use a platinum. So that will reduce the carbonyl of this ketone, which is attached to benzene, to a CH2. So bromine comes here, and then this becomes a CH2. Now, what do you do now? This is now a para-director, auto-para-director. Now you do your what? Sulfonation, exactly. Now you do your sulfonation. Sulfur trioxide in the presence of sulfuric acid, and then you do. So the choice of sequence is most important in this particular problem, because then you need to know, take account of your directing influence for all of the substituents, okay? Because if you start with the wrong sequence, then you will not get to your product. Okay, and that is this product right here. 2-bromo ethylbenzene sulfonic acid. Okay, folks, we have come to the end of today's session. And for those of you who want to ask me additional questions, I will stay around for another 5 minutes. Offline, I am going to turn off the recording now, so the question that you ask me will not be recorded. Okay, so for those of you who are leaving right away, enjoy the rest of your evening, and I will see you tomorrow. Unless you have a question, by the way. Is there any question? No question. Okay. So let me go ahead and cut off the recording.